Hi, welcome to the recitation session for week 7. On this occasion, I will be discussing steady state error for tracking purpose. So what is tracking? Tracking is one of important tasks in control system, and the objective of tracking is to track a certain reference signal. For example, you want the output for your system to match the desired set point. So let us consider the following system. So I have a transfer function and the output is y of s. So this is in Laplace domain, and we have input u, and also the system is configured with a feedback system. We have a negative feedback, and let us define the error as this signal right here. So this is a system with unity feedback, and the purpose of tracking error, or the purpose of tracking, is we want to have the limit as t goes to infinity u of t, so in time domain, minus y of t is equal to 0. Okay, so basically we want the output to be equal to the input as time goes to infinity, and this is equivalent with having limit t to infinity with error approaching 0. Okay, so here error is defined as the difference between the input and the output. All right. So u, sometimes it is referred to as the reference or the set point, and it can be any signal like step function, ramp function, and so on. So basically, u can be configured or can be type of a piecewise constant signals, and this is a typical system when we have a tracking. So we will have a unity negative feedback control system. And what is steady state error then? So steady state error, or ESS, is defined as the value of e of t as t goes to infinity. Okay, so if there's no error, or when the output matches the input value, then we have the steady state error to be equal to 0. And assuming that the system is stable, so assuming that the closed loop system is stable, then by using final value theorem, the steady state error can also be computed by limit s approaching 0 with s multiplied by e of s. Okay, so we can use the equation on the right if the system is stable. As I mentioned before, then there are three basic types of control input. So there are, first one, step. So I guess you guys are already familiar with step input. So step input is u of t is defined as 1 for t greater than equal to 0. So if you plot it, it's just this is t, this is u of t, then step function is just 1, so has value of 1 for t greater than equal to 0. Or in Laplace domain, u of s is 1 over s. You can get this is from the Laplace table. The second type of input is RAM input. U of t is equal to t for t greater than or equal to 0, and RAM input looks like this. So it's just a linear function as, and it is keep increasing as t goes to infinity. In Laplace domain, u of s is 1 over s squared. The next type is acceleration. It is characterized by u of t equals to 1/2 t squared for t greater than or equal to 0, which is in Laplace domain is 1 over s cubed. So it is a quadratic function, looks like this, t u of t. Okay, so in this lecture I will be discussing what is the corresponding steady state input, the steady state error given these three different inputs. Okay, to do that we need to assume the following. So the transfer function, the assumption on g of s is that g of s has the following structure. G of s is it has k constant gain, and it has some polynomials ta. So on the numerator there are m degrees of polynomial, so say k p numerator. So p numerator is just this polynomial with degree m, and on the denominator we have s. So s is the Laplace variable, s to the n, and also some polynomial with degree n. So s to the n, so this is capital N, but the degree of this polynomial on the denominator is, this is degree m, and this one is degree n. All right, the question is, what is the steady state input for a given reference point or input signal? So here let's find out the answer of this question. Okay, so in frequency domain or in Laplace domain, we want to find the transfer function between the error and the input, right? Because if we know the input, then we can determine the error. So what is E of s? E of s is here. So E of t is u of t minus y of t. So E of s is nothing but u of s minus y of s. U of s minus y of s over u of s. So this one minus y of s over u of s. But we know that y of s over u of s is the transfer function of the closed loop system. Y of s over u of s is g of s over 1 plus g of s. Okay, so continue with this. We have g of s over 1 plus g of s, which is 1 plus g of s over 1 plus g of s minus g of s over 1 plus g of s. So we get 1 over 1 plus g of s. Okay, so this is the transfer function of e of s over u of s. From here we get e of s is u of s over 1 plus g of s. Okay, so we will determine the steady state error for these three different types of inputs, and assuming that the system is stable, then we can use the final value theorem. So we will use this equation right here. Okay, let's do that. Okay, I didn't mention that g of s is said to be type of n. So n is the power of s here. So we have basically we want to examine three different types of g of s. So for n equal to 1, 2, or 3. Okay, so for g of s of type 1, g of s of type 2, and g of s of type 3. For system with type 0, sorry, this should be type 0, 1, 2, type 0, or n equals to 0. Then the steady state error is, assuming that the closed loop system is stable, then s e of s, right, which is s u of s over 1 plus g of s. Alright, for the first kind of input we have step input. Then the steady state error is limit s to 0, and u of s is step, so step is 1 over s, 1 plus g of s. So limit s to 0, 1 over 1 plus g of s. And if I define this way, kp, then kp is limit s to 0 g of s. Okay, how about RAM input? So what is the steady state error of type 0 system with respect to RAM input? So we have limit s to 0, s over 1 plus g of s, but since u of s is RAM input and RAM is 1 over s squared in Laplace domain, and we have 1 over s squared, which is limit s to 0 1 over s 1 plus g of s, which is infinity. Okay, and how about acceleration input? So limit s to 0 1 over s cubed 1 plus g of s. Again, we have s to 0 1 over s squared 1 plus g of s, and we obtain infinity. Okay, so in summary, for type 0 system, so when we have this kind of system, closed loop system, where g of s is type 0, so g of s has this form with n equal to 0, so we don't have any roots on equals 0. Then if we give the system with step input, then the steady state error is given by this formula. But for ramp or acceleration input, then the steady state error is infinity, meaning that the system cannot track input with ramp or acceleration because the error is infinity. So it is impossible to track ramp or acceleration for type 0 system with unity feedback. Okay, how about type 1? For type 1, where the roots of g of s, which is equal to 0, has 1 root, so for n equal to 1, then step input ss is limit s to 0. Again, we have s multiplied by the step 1 plus g of s. Okay, limit s to 0 1 over 1 plus. Let's see here that for type 1 system, then g of s has the following structures. Okay, the polynomial on the numerator over s times polynomial on the denominator, which is limit s to 0 s over s plus kp, which is 0. So okay, so it's telling us that for type 1 system, then if we are giving it step input and the closed loop system with unity gain feedback, it can provide a really good tracking, or it can give us an almost perfect tracking because the input um, can match with the output. For RAM input, then the steady state error is one plus g of s. Why 1 over s? Because s times 1 over s squared. Okay, so this is nothing but limit s to 0 1 over s plus s g of s, and since s is 0, then this is just limit s to 0 1 over s g of s. And if I define this as k phi, then k phi is limit s to 0 s times g of s. Okay, for acceleration, the steady state error is limit s to 0, we have 1 over s squared 1 plus g of s, limit s to 0 1 over s squared plus s squared g of s. So limit s to 0 1 over s squared, and g of s for type 1 has this structure, so k p numerator s p denominator. So limit s to 0 1 over s k p numerator, and this one is p denominator. So we know that this is infinity. So for type 1 system, if we are giving it acceleration input, then the closed loop system cannot track the input since the steady state error is infinity. The last type is type 2, or n equals 2. What happens if we are giving it step input? Then the steady state error is limit s to 0, we have 1 over 1 plus g of s, right? But remember that we have limit s to 0 1 over 1 plus, and g of s is of type 2, so we have k p numerator over s squared, because it is type 2, p denominator, limit s to 0 s squared p denominator, this one s squared p denominator plus k p numerator, which is 0, right? So for type 2 system, it can track step input perfectly. How about RAM? For this, limit s to 0, we have 1 over s plus s g of s. So limit s to 0 1 over s plus s, and g of s is k p numerator of s over s squared p denominator of s. So s cancels, which is limit s to 0 multiply the numerator and denominator with s times p denominator. We have s p denominator over s squared p denominator of s plus k polynomial on the numerator. Again, this is equal to 0. For acceleration, the steady state input is is limit s to 0 1 over s squared 1 plus g of s, right? And this is equal to s to 0 1 over s squared plus s squared g of s, which is limit s to 0 1 over s squared g of s. So this is not 0, right? Because it's type 2, and in type 2 we have s squared over here, so s squared over s squared cancel, and so I can define this as Ka, where Ka is limit s to 0 s squared times g of s. Okay, so in conclusion, we have this table, so let's construct the table. Okay, so this is the type of input step. This is ramp, acceleration, and this is the type of the system: type 0, type 1, and type 2. For type 0 system with step input, then the steady state error ESS is 1 over limit s to 0 g of s, or Kp, and for RAM the error is infinity. The same with acceleration input. For type 1 system, then the steady state error with step input is 0, so we have 0, and the steady state error for RAM input is 1 over the limit this will be 1 plus limit s to 0 g of s, but for this one is limit s to 0 s times g of s, and this is infinity. For type 2 we have 0 0, and this one is 1 over limit s to 0 s squared g of s. Okay, let's have a simple example. Say I have the same system g of s with unity negative feedback. The reference R, you have error over here, and the output is C, say it's C of s, this plus, and G of s is given as follow: 100 s plus 2 s plus 6 over s plus 3 s plus 4. Okay, so given G of s, then we can immediately see that the type of this system is type 1. See, so this is type 1 because we have poles that is equal to 0, only one pole, so we know that g of s is of type 1. All right, and the question is, find the steady state error for u of t equals 1, which is step, u of t equals t RAM input, and u of t equals to 1/2 t squared, or acceleration input. Let's solve this. first the first step is we need to determine if the closed loop system is stable, right? Because if the closed loop system is unstable, then there's no point of analyzing the steady state error because the system is unstable. For unstable system, then the error will be infinity. So first, let's us determine the stability of the system. So we need to find first find the roots of the closed loop system. C of S over R of S. And C of S over R of S is what? Okay, it's G of S over 1 plus G of S, which is what? It's 100 S plus 2 S plus 6 over S plus 3 S plus 4 plus 100 S plus 2 S plus 6, right? And this is equivalent to 100 S squared plus 8 S plus 12, and the denominator is S cubed plus 107 S squared plus 812 S plus 1200. Okay, so is this system stable? So you can compute the roots of this polynomial. So this polynomial, the roots are minus 98.9, minus 6.1, and minus 2. Okay, so the closed loop system is indeed stable. Hence, we can analyze the steady state error. Okay, we can use the table for, so since this is type 1, then we can focus on this row. For step input, we know that steady state error for type 1 is 0. Okay, that's definitive. How about RAM? Then ESS is 1 over limit s to 0 s times g of s, right? Which is 1 over limit s to 0. So s times g of s is 100 s times 100 times s plus 2 s plus 6 over s plus 3 s plus 4. So s and s, they cancel. We just need to evaluate this. So as s equals to 0, then we have 100 to 6, and here is 3 4. So this is 3 4, 3 and 4, 3 and 6. The remainder is 2, and 2 times 2 is 4. So this is only 1 over 100. Okay, so the steady state error for the system with random input is 1 over 100, or 0.01. How about acceleration input? So we know that for acceleration input for type 1 system, then the steady state error is infinity. so just infinity. Okay, so that concludes the lecture for today. I hope you guys can follow, and if you have any question, then do not hesitate to email me, and I'll see you next week. Thank you.